Okay, more students coming in. And today is Monday, May 11th. Let's take a look at the syllabus. Today's Monday here, May 11. We started the mirrors last time. We continued on the mirrors last time we finished, right? And now we're going to start refraction 1 here. And hopefully, I don't think we'll start relativity today, but let's see how things go. I'll have to share my screen, right? Okay, here you go. Monday, 11th of May, the 14th week, the 24th meeting. And we are writing here. Like I said, I don't think we'll be able to start relativity. So let's move it here. Refraction. And you see more students coming in. And that's the notes view. Let's take a look at the date of the third exam. Third exam is gonna be next week already. Okay, yeah, next week already. Okay. So we covered up to, let's see if we finish chapter 26, right? And we get those two here. For the labs, let's put the lab 4 for now. Labs 3 and 4. I'll let you know if there will be more labs in this third exam. And Ariane is coming in. This is the notes of last meeting, May 11, 26, Monday. Fourteenth week, 24th meeting. 14th week, 24th meeting. And we finished chapter 25, right? And now we are going to start chapter 26 for exam 3 so far. Yeah. And more students coming in. Refraction. This is of refraction. Okay, so section of chapters 26. Let's see if we can. I'd rather, include chapter 26 in exam 3, but I'm not sure if we're going to be able to do that. Okay. So, but it looks like a very extensive chapter 26. Let's, for now, let's Let us skip for the exam up to chapter 25. Okay, if I change my mind, if we get enough time to cover everything, we will change to 26. Okay, so sections. This I'm going to close lab. Here you go. And what we are going to do here, we are going to define a quantity that we call the index of refraction. It's a very important quantity in optics. And then we're going to talk about the Snell's law, law between quotes. It's not exactly a law. And there is a quantity, there is a very important quantity in optics called there is a very important quantity in optics called the index of refraction, which is also referred to as the optical density. The optical density. The higher the optical density, here you go, the higher the index of refraction, comma, the slower the light propagates through the medium. Okay? It's a very important quantity in optics called the index of refraction. This quantity is associated with a given medium through which the light propagates. This quantity, right, is also referred to as the optical density. Optical density is equal to the index of refraction. Index of refraction. The higher the optical density, the slower the light propagates through the medium. And that's the idea of index of refraction. Is, like I said, the optical density. And how is the definition, right? Definition of index of refraction. Definition of the index of refraction. It's defined in terms of the speed of the light. Speed of the light in vacuum divided by the speed of the light in the medium. Index of refraction of a given medium. Of a given medium. Index of refraction n of a given medium. Light in the speed of the light in the vacuum divided by the speed of the light in the medium. That's how we define it. We can also measure it. There are ways to measure it. From this definition, it's straightforward to see that the refractive index of vacuum is 0. And how do we do that? We know what's the speed of the light in the vacuum, right? Here you go. The speed of the light in the vacuum is c. And if we replace the denominator with c, we get the value 1 for the index of refraction. The case for the index of refraction of the air is rather similar. for the index of refraction of the air, we have a similar result. Okay, the index of refraction of the air is very close to the index of refraction of the vacuum, because the speed of the light in air is just slightly less than the speed of the light in the vacuum. So here we go. N of air is approximately equal to C over C. So it's very close to the index to the speed of the light in the vacuum, okay? It's slightly less. By the way, you're going to see that the index of refraction of the air is slightly more than the index of refraction of the vacuum. Strictly speaking, right? Strictly speaking, the index of refraction of the air is just slightly more than the index of refraction of the vacuum. And then we have other mediums, other types of mediums. Here go, like, oh, here you go. For the air, it's not one, right? It's just slightly more than one. See here? It's man, this is 0.3% higher. Huh? That here should be 1%, 0.1%. Oh, 0.03% higher than the index of refraction of the vacuum. So that's why we can come up with this approximation right in here, because the difference is slightly less. Okay. We have other optical substances out there. You can look at the table of the refractive index for different optical substances. Some of them are easy to memorize, like the index of refraction of the water, 1.333. Most glasses have a refractive index of 1.5. Diamond has a refractive index of 2.42. Sapphire, which is a precious stone, has an index of refraction of 1.77. Substances should be plural. And then there's a bunch of other optical materials out there. You don't have to memorize every one, but I suggest that you memorize those two at least: the vacuum, the air, the water, and most glasses. Most glasses and plastic. The other ones is just for your own curiosity, okay? Now, so note that light travels with different speeds in different media. This characteristic results in a series of interesting types of interesting behaviors for the light. Behaviors for the light that we are going to cover here. Okay? So note this characteristic, right? Like that. So let's see. Reflection is different from refraction, okay? Don't forget, reflection is different from refraction. Reflection, light bounces back from the incident surface. Light bounces back from the incident surface. And refraction, light enters, okay, propagates towards a different medium, enters or propagates towards a different medium. Now, when light enters a medium of different refractive index, it may change its direction of propagation. Not only its speed, it changes not only its speed, but also it changes not only its speed, but also, it may also change its direction of propagation. Go, and let me show you that now we came to a point that I'm going to show you some illustrations here. Illustrations right in here. Magnetic field, reflection, mirror, refraction, and lenses. Here you go. So here you go. We have a source, a light source. You already know that light travels in a straight line. Caramba. Here you go. You already know that light travels in a straight line from S to C, from S to A, from S to B in an optically homogeneous medium. Okay, here we do not have, but however, and this type of behavior is consequence of the least speed principle, the principle of least speed. Not only it can be used for reflection, but the principle of least speed, least time, right, can also be used for refraction. If we introduce a second medium of different refractive index, what do we find out? We find out that if the light is going to move from point S to point B here, it's not going to be in a straight line path. Okay, this dashed line here is the path of least amount of space, right? Is the path of least space, or even least distance. Let's put like that, distance. Path of least distance. But nature does not follow the path of least distance. Nature follow the path of least time. Path of least time. Or this time, right? So how does it do? It moves in this direction right in here, and then is refracted. Is the light refracted? The light is bent towards that point B. That's how light behaves. The same applies to the other points. Okay, S to A, right? S to this point A here. Path of the light from a medium of low refractive index to a medium of higher refractive index. Notice that light is being bent towards the normal. And when light is propagated from a medium of higher refractive index to a medium of lower refractive index, it's bent away from the normal. That's how it behaves, okay? If light is incident normal to the surface, it doesn't change direction. You just move in a straight line. Okay? This is the qualitative treatment. And there's more. Not only light refracts, but also light reflects at this interface. Do you see here? The source is right in here. The light is moving towards the interface between, the medium and the air. Not only it refracts towards the medium, into the medium, but also it reflects at this interface. And if you keep on increasing this angle of incidence, here's the angle of incidence, right? We can start to see that light is moving away, right? The light that refracts into a medium of lower refractive index is bent away from the normal, but we still have reflection as well. It's not total reflection, it's partial reflection. And the law of reflection also applies. Angle of incidence is equal to angle of reflection. Okay, the question here, how do you find out the angle of refraction? Okay, that's the question that you gotta make to yourself. You wanna ask yourself. Okay, for the angle, here you go, for recall the law of reflection. The angle of incidence is equal to the angle of reflection. Which we can denote with the following formula, like that. Theta, angle of reflection, is equal to the angle of incidence. Okay, that and then we also have the law of refraction, which is also referred as Snell's law. Okay, and how is it spelled out? It's easy to memorize. I'm not going to prove that, but it's possible to prove it using the principle of least time. Okay, so we are going to have the angle of refraction. Let's put refraction. Here should be reflection, right? Angle of refraction is not going to be equal to the angle of incidence. No. The equation is a little bit more difficult, okay? So should be, I'm going to put like that on the right side as well. Index of refraction of the first medium times the sine of the angle of incidence is equal to the index of refraction of the second medium times the angle of refraction. That's how you find out the angle of refraction as a function of the angle of incidence. I'm putting N1 sine theta incident and 2 sine theta refraction. Okay, so here you go. That's my angle of incidence. And that's my angle of refraction right here. And again, if light is going from a medium of high refractive index to a medium of lower refractive index, light bend outwards. The refracted light is going to, the light is going to be refracted at an angle that's greater than the angle of incidence. And likewise, if light is going from medium of index of refraction that's lower than the index of refraction of the other medium, light is going to be bent towards the normal. Okay, so you go, that is already implicit here in this equation. Okay, so note C from the above. Note C from the above. Note C the following from the above, right? From the above. If N2 greater than N1, right? What's gonna happen? You know, if N2 greater than N1, we have the following, comma, we have the following. I'm gonna pass N1 to the other side, right? And then I'm gonna pass the sign of refraction to the other side as well. What we are going to have, we just analyze what we have right in here. And so what does it mean? N2 over N1 is going to be greater than 1, right? If N2 greater than N1, it means that the ratio in the left side is going to be greater than 1. And if we have this relationship, we also going to have this relationship here for the angle of incidence and the angle of refraction. What does it mean? It means that this sign is going to be greater than this sign, right? The sign here is going to be greater than the other sign, which implies that the angle of incidence is going to be greater than the angle of refraction. That's a result that is already implicit into this law, into Snell's law. And then we can repeat that, the same thing, for the other case, right? If N2 less than N1, we have the following. Okay, here all you have to do is to change this inequality. We gotta change this inequality. Change this inequality. And the angle of incidence will end up being less than the angle of refraction. I'm proving mathematically that that's how it behaves, right? But what about normal incidence? What about normal incidence? Or what about if the angle of incidence is equal to 0 degrees? Okay, so here we go. Oh, all you gotta do is to use Snell's law. Here we go. Get this equation. Put a question mark here. So here we go. Normal incidence. The angle of incidence is going to be 0. So the sine is going to be 0. Okay. A non-zero number multiplied by 0 is going to be 0. All right. And the left side must be 0 as well. And 2 is not 0. And 2 is not 0. Okay. Because it's a medium, there's no such a thing as a medium is a 0 refractive index. So what's going to be 0 is going to be the sign of refraction. And the angle of refraction, if the sign of refraction is 0, it means that the angle of refraction is 0 as well. Okay, so put side by side those laws. I already did that, right? So let's see here. Already did that. Yeah, here you go. Those two laws. One is the law of reflection. The other one is the law of refraction. Okay, it's not difficult to memorize that, right? The law of refraction. Now we have an important special case for this, for the angle of refraction that I'm going to show to you right now. Here you go. Light coming, remember, suppose that we have light propagating inside a medium of higher refractive index, right? As light is incident at the interface, the light is gonna be bent away from the normal. So that's what you have right in here. The reflected light is still gonna have the same angle of refraction, right? What about here? Here you go. As I increase the angle, something interesting is gonna happen. As I increase the angle of incidence, the refracted light moves further and further away from the normal until it comes to a point where none of the light is refracted towards the medium. Instead, light is going to propagate exactly at the interface between those two media. This phenomenon has a name. Okay? Under this situation, what we're going to have, we're going to have what we call total internal reflection. No refraction occurs, okay? Total internal reflection. And now that we have total internal reflection at this angle, light can propagate for very long distances without much loss, okay? And you have already seen an illustration of mine, right? In my website. Here is my website, Waveguide Kits. If you go to Waveguide Kits, you can visualize this type of phenomenon. Light is incident at this angle here, right? Angle of incidence, and it gets bent towards the normal. Okay? And when it propagates towards the medium of lower refractive index, light gets bent away from the normal. This angle of incidence is less than this other angle of refraction. And you have here the path of the light. And also notice that at every reflection, light loses some of its intensity, right? Because it's leaking out. It is like a pipe in which water is leaking out. Higher intensity, lower intensity, and so on. You see what's happening here? Here is reflection, here is refraction. Here is reflection, here is reflection, here is refraction. Another reflection. This reflection is associated with this light ray right in here. Reflection, refraction. And we still have a little bit of a ghost light, right? Let's see if I can. A little bit difficult to see. And so on, okay? Now, there is a very interesting phenomenon, the phenomenon of total internal reflection, that you can visualize right in here, okay? This is a patent of mine. I managed to patent this type of effect that you see right here. If you have an optical medium that's tapered like that, instead of that bar, eventually this light that's trapped here inside this bar is going to achieve total internal reflection. Initially, it doesn't achieve total internal reflection. You can see, right? So here you go, light here, the incident is reflected. Some of the light is coupled inside the bar, right? The taper. But we still have some light leaking out. But eventually, because this angle of incidence is increasing, okay, due to this taper that we have here, the angle of incidence at the interface keeps on increasing. Because of that, eventually, the light becomes totally internally reflected inside this waveguide, which is similar to what you saw here in this illustration, okay? The only difference here that we have to change the angle of incidence of the light, whereas in the other case, the angle of incidence of the light is automatically changed because of the taper. And when we have something like that, you know, total internal reflection, like I said, light propagates to much longer lengths. Okay? So let's write that down here in our notes. Okay, when light is incident from a medium of lower refractive index towards a medium of lower refractive index, comma, its angle of refraction decreases. The opposite is true as well. Due to Snell's law. And the opposite is true as well. When light is incident from a medium of higher refractive index towards a medium of, wait a minute. Oh, here you go, higher, here you go. I made a mistake here. Higher refractive index towards a medium of lower refractive index, its angle of refraction increases, also due to Snell's law. In this second case, we have an important consequence. Okay? As the angle of incidence increases, comma, the angle of refraction increases further. until it reaches 90 degrees. At this point, we have what we call the phenomenon of total internal refraction, TIR, or TIR, total internal refraction, or TIR. The angle of incidence, let's put another paragraph here, at which we have TIR, the angle of incidence at which you have TIR, or the angle of incidence at which the angle of refraction is 90 degrees. Is 90 degrees. It's called the critical angle. So the situation goes like that. Here you go. Get Snell's law. When the angle of incidence is equal to the critical angle, here you go, it's called theta C, then the angle of refraction becomes 90 degrees. Okay? So we can find out what this angle of incidence is going to be when sine when the angle of refraction is equal to 90 degrees, its sine is going to be 1, right? We have this situation here. And we also have let's not forget, in this case, N1 is greater than N2, right? N1 greater than N2. And now, you go. That holds, right? Because sine is always, here you go, N2 less than N1, it means that this ratio is less than 1, right? And that holds because sine of an angle will always be greater, less, or equal than 1. Let's put like that, less or equal than 1. The critical angle is going to be the arc sine of this angle. Like that. Got the idea? That's the equation for the critical angle. When theta is greater or equal than theta critical, we have total internal reflection. TIR, let's see. Oh, it's not total internal refraction. It's total internal reflection, right? Reflection. 100% of the light is reflected. That's what it means by total internal reflection. At this point right in here, we have that 100% of the light is reflected. That's why you call it total internal reflection. Total internal reflection here, total internal reflection here, and so on. Here now, here is a percentage. Okay? And we can determine this percentage from another set of equations that we are not going to cover here. And that's the way optical fibers behave. A second medium of lower refractive index around the medium of higher refractive index, right? The interface between these two media can reflect the light if the angle is greater or equal than the critical angle. In the case of water, in the pool, in the swimming pool, we have total internal reflection for a given angle of incidence. And we can calculate that, right? Let's take a look. Example. Let me change that here, symbol. And now we can come up with a nice this one here. I want to put insert symbol. Yeah, this one here. That's what I want. Okay, example. Find the critical angle for a light beam that is propagating inside water and is incident at the water air interface. Okay, so here you go. The equation is this one that you see right in here. The equation for the critical angle. We do know that the index of refraction of the air is 1, and the index of refraction of the water is 1.333, right? Here is 1, here is 1.33, 1.333. And we can take the arc sign of this quantity. Let's take a look at the let me quit those. Ew. Let's see this one here. Do I have more? Let me first open the roster. We can calculate it. Here we go. Let's get this one. Okay, zoom view 200%. Okay, N1. Oh gosh. N1 format subscript N2 N2. Let's see if I got it right. we reserve N1 for the first medium, right? Let's see here. Let's see if I got it right. Yeah, okay. N2 is going to be air. Air. N1 is going to be water. And we want to find out the critical angle. Yeah. And now subscript here. Okay, and we go ahead and arc sine, right? Arc sine of 1 divided by this. And what we should get should be in radians. That's radians. And now if we want to change to degrees, so we use this function and we get 48 degrees. Okay, once this angle here reaches 48 degrees, 48.6 degrees, then we're going to have total internal reflection. That's an example. And you can do the same for other types of refractive index, right? Let's see here, 1.5 refractive index for the glass. And we can get that the critical angle, why it didn't work? Let's see here. Oh, I know why. I should be 1 here. Yeah. Glass surrounded by air, right? Glass surrounded by air. And now the critical angle is less stringent, is less strict. It's 41 degrees because the refractive index is greater. Okay. One 1.33, 1.5, and so on. And so on. Okay. Let's quit this one here. Oops, cancel. I don't want that. Let's see here. Yeah, let's save each one separately. Save it. Continue. That's 10:38, right? Very soon we're gonna have our break here. Let's see what else we have here that I can cover in the next few minutes. Next 2 minutes. Total internal reflection. Remember that. And here you go. That's the material you have covered so far, index of refraction, Snell's law, and total internal reflection. We didn't cover dispersion yet, but we're going to do that soon, okay? We're going to skip polarization by reflection, refraction. And we can now have our break. Break 10:38 a.m. to 10:48, no, 53, 10:53 a.m., right? Yeah, let's now it's already 39:54. Any questions? Let's see if you have any questions. No. So I see you in 15 minutes. Thank you. Let's see. I'm back here. The next topic is going to be dispersion of light. We're going to skip polarization by reflection and refraction. And what is dispersion of light, right? What is dispersion of light? Okay, and the answer is simple. Different dispersion of light is a phenomenon in which different wavelengths, different light wavelengths, right? Different wavelengths of light experience, right? Experience a different index of refraction. That's what it is. Okay, so example, right? Blue light, example. Blue light. Which has a wavelength of around 450 nanometers. Let's make sure. Wavelength of blue light. Of blue light here. It's a region, it's a between 380 and 500 nanometers, okay? Blue light. Between 380 and 500 nanometers. 400, I use like 450, for instance. For instance, blue light, which has a wavelength of 450, comma, sees, experience, right? One refractive index, whereas red light, I'm gonna use 600 nanometers of wavelength, of 600 nanometer wavelengths, experiences another index of refraction. Index of refraction in the same medium. So the index of refraction depends on the wavelength of the light. That's what dispersion is all about. Because of that, the angle of refraction of two different wavelengths will be different. And we have an illustration here. Here you go, right in here. So if you have white light is made up of all wavelengths. Okay, that's why we see white. We see white because it's a combination of red, green, and blue and other colors. So when we shine white light in this medium that you see right here, what's going to happen? Some of the light is going to be the angle of refraction of different colors is going to be different. In this specific case, the angle of refraction of blue light is less than the angle of refraction of the red light. And that's what dispersion is all about. Dispersion allows you to separate different wavelengths coming from a given source. Okay? That's what dispersion is all about. In the case of the blue light, the index of refraction that the blue light experiences more than the index of refraction of the red light. A blue light is more affected than red light in terms of refraction. Note C and note C that let's see, the dispersal light is a phenomenon in which different wavelengths of light experience a different index of refraction. Has a wavelength 450, and it experiences a larger refractive index, whereas experiences a lower refractive index of refraction compared in the same medium. And you can see, there are, let's see here. There are catalogs out there that documents the dispersion of light. And let me show you here. What's the name of the company? Shot, yeah. Shot Glass has a very nice catalog that documents the dispersion. Shot Glass catalog. Let's see, right in here. Shot download. Okay. Shot Glass, they commercialize different optical glasses out there, and they are very thorough on their data sheet. Okay, here you go, data sheet of their glass. Data sheet, collect optical glass. Let's see if we can have pressed blanks. Let's see which one we're going to look at. Optical materials and precision mode. Let's try to take a look at this one. Here you go. That's the document, one of the documents shot. Okay. Optical glasses. Those are all types of glasses that they have out there. And all of them have a refractive index that is around 1.5, between 1.4 and 1.5, okay? Each line that you see here is a different glass. And let's see, looks like we got it right in here. This one here that I want. Internal transmittance, refractive index. That's the one we want here. Okay, at different wavelengths, you can see that we have different indices of refraction. If you shine light at 404 nanometers, the refractive index is going to be 1.49, right? However, if you increase the wavelengths all the way up to red, around here, the refractive index is going to be 1.48. Let me here you go, 1.48. Right, here you go, 300, 404. The difference is small, okay, but might be enough to look at the refractive index at 280 nanometer. That's ultraviolet, okay? It's 152, 1.52. That's what the dispersion is all about. In the infrared, 230, 232, 2,325, not, okay? 2,325 nanometers, 1.46. Okay, and that's what dispersion is all about. And we have, that's one glass, that's just one of their glasses, NFK5. And there are others, right? There are other glasses. If you go through this catalog, BK7 HT. I used to buy those glasses to make optical fibers. Here you go. From this other glass, from 312 nanometers to 2300 nanometers, right? It goes from 154 to 148, and so on. Okay, you can, let me give you the link for the site of theirs. Shot glass. Shot glass has an extensive catalog of different glasses that documents the dispersion. There's a catalog that documents the dispersion of different glasses of the glasses they manufacture. See, for instance, this one here. See, for instance, oh my goodness, that's not what I want. Let's try it again. Copy. Paste. Okay, now we got it. That's what dispersion is all about. Okay. So in general, the refractive index, because the refractive index decreases with the wavelengths, we can say, okay, in general, the refractive index decreases with the wavelengths. Or you can write like that. The refractive index is a function of the wavelengths. It's inversely proportional to the wavelengths. Okay, so let's take a look what the book says about that in about dispersion, right? Wild course resources. Chapter 26, right in here. Index of refraction, we covered. Snell's law in the refraction of light. Okay, derivation of the Snell's law. I didn't do that, okay, because it takes some time to do that. If you want to take a look how to derive the Snell's law, you can take a look here. Total internal reflection, we covered. Total internal reflection is used to image the inside of the body. We skip the polarization. And here you go, it's dispersion. Okay. So light goes inside the prism and then is refracted twice, right? It's refracted once it enters the glass, and it's refracted again once it exits the glass. That's a dispersion. Here you go. Refractive index decreases with the wavelengths. Red has a lower refractive index than violet and blue. That's for the crown glass, a type of glass that's all we have out there. And that's what it's dispersion that allow us to see the rainbow. And the material that disperses the light is going to be the rain drops, the rain droplets. So light is refracted inside the raindrop. It gets reflected on the inside of the rain droplet, and then is suffer dispersion again once the light comes out of the rain droplet and forms this nice display of different colors. Okay. Now we can start talking about lenses. So the situation now is the following. We covered dispersion. And now we're going to cover spherical lenses. Remember that we covered spherical mirrors. Now I'm going to cover spherical lenses. Okay. So in this chapter, we will introduce the very basic ideas of seeing spherical lenses. Whatever you do here is going to be for thin lenses, not thick one. And the thickness and thin lens is defined in terms of the diameter of the lens, diameter D, capital D. The thickness must be much less than D. And by much less than d, what do we mean by much less than d? Thickness must be less than 1/10 of d. D over 10. Let's put this way. Italics. Italics. The theory of thin spherical lens is a very good approximation of most real-life lenses. This section is very similar to the one that we covered for mirrors, although it's more involved because it involves refraction. The device is different, light behaves differently, but the final formulas are the same. Okay, and that's an amazing thing, right? The formula for the position of the object and the image, and what I mean. But the final formulas and the formulas related to the position of the image and its magnification are the same, okay? So we have different types of lenses. Planar convex is a positive lens. Planar concave is a negative lens. Biconvex, biconcave, and concave convex lenses. Let's get that here. Here we go. Okay, here light rays. What I want to show you is this one here. Here you go. It's spherical lens, right? Don't forget. How do we form a spherical lens? Okay, we come up with a surface, a spherical surface of radius r, and that will be one surface of the lens. If the other surface of the lens is planar, it means that its radius of curvature is very large, goes to infinity. So what you see here is a planar convex lens. Planar convex lens. But there, like I said before, there are others, right? Planar convex, planar concave, biconvex, biconcave. Planar concave, you know, this surface is going to be concave, planar concave. The biconvex surface, we have a convex surface on one side and another convex surface on the other side. Biconcave, we have both surfaces are going to be concave. And concave convex lens would be, you know, convex surface here and a concave surface here. 5 different types of lenses, of spherical lenses. And how do we deal with it? We do it mathematically, we do it exactly in the same way we did with mirrors. You do a drawing of the lens, come up with the principal axis of the lens. Here is a collimated light ray, a light ray that's parallel to the principal axis. And this light ray is incident in the lens, on the lens surface. Okay, and because this is a planar surface and the light ray is parallel to the principal axis, the light doesn't suffer any refraction whatsoever inside the lens. This light ray, okay? But when it reaches the other side of the lens, it will refract because its angle of incidence It's not going to be zero. It's not going to be 0 degrees. It's going to be different. Okay, in this specific case, the light ray is going to be bent towards the normal. Okay, so here we go. Not away from the normal, sorry, away from the normal because it's a lower refractive index. Okay, and that's the light ray right in here. Because the light rays are parallel to the principal axis, this light ray, right, after refracting from the lens, must pass through the focal point of the lens. Must pass through the focal point of the lens. Another collimated light ray. Collimated means parallel to the principal axis of the lens. Is going to be bent towards the focal point as well. So we have images that are formed by the lens as well, just like we had images formed by the mirror. That's a representation of a positive lens. A lens that focuses the light. That's what a positive lens is all about. Is a lens that focuses the light, okay? The representation of a negative lens is something like that, but with arrows in the other direction. Here's the representation of a negative lens. A positive lens can be a biconvex lens, can be a planar convex lens, and so on. A negative lens can be a planar concave lens or a biconcave lens. So here you go, positive lens. Principal axis is not much different than what we did for mirrors. We mark the focal point of the lens. The lens, don't forget the lens have two centers of curvature, right? And because the lens has two centers of curvature, we're not going to display the center of curvature here. We have this other focal point in front of the lens and the object. Light parallel to the principal axis is bent towards the focal point behind the lens. Light passing through the focal point in front of the lens must bend in a direction that's parallel to the principal axis of the lens. And here is the image that's formed. Okay, so it's a real image, real inverted image. We can draw a third light ray that passes through the center of the lens and passes unrefracted. Okay, that's the distance of the object. That's the distance of the image. Here you go, that's the focal distance of the lens. Okay, and this equation and the equation for the object is the same one that we got for the position of the image, the same one that we got for the mirror, okay? All these lenses may produce a real or virtual, or improper, real, virtual, or improper image, just like the mirrors we covered before, okay? And just like the mirrors, we also have a given lens. A given lens also has a focal point. Since the lens surface have two radii, since the lens, let's see, since the lens has two surfaces which may have different radius of curvature, comma, we don't define a center of curvature. The light rays we can use up to 3 light rays to identify the position of the image for a given object. One, light rays, collimated light rays that are parallel to the principal axis of the lens and is refracted towards of the lens. Light rays that pass to the center of the lens. These light rays do not change their direction of propagation. Okay. What else? Light rays that pass through the focal point in front of the lens and refract parallel to the principal axis. 3 light rays that can be used to find out the position of the image of a given object. Let's save some space here, right? Here we go. And I'm going to change start 1. three different light rays. The position of the image of a given object can be obtained from the same equation we got for mirrors. And what is this equation? Okay, the equation is going to be 1 divided by F is equal to 1 divided by D naught plus 1 divided by the image. Same equation. But don't forget, that's for C lenses, okay? If the lens becomes thick enough, this equation must have a correction term there. But we are not covering that here. We're covering only C lenses, the samples of all lenses that are going to find out there. And in addition to that, we also have that H naught over HI is equal to minus D naught over DI. And right? That's the side of the image. The negative sign that tells you if the image is inverted or not. Magnification. What about the magnification? 1 divided by magnification, right, is equal to that. But let's not forget is the magnitude of that as well. Here go this one here. Because it's the magnitude, this negative sign disappear like that. The magnitude term is the HI, right? The height of the image in terms of the height of the object. So here go. We have similarities, right, and differences between mirrors and lenses. You know, a concave mirror concentrates collimated light rays, whereas a concave lens diverges collimated light rays. A convex mirror diverges collimated light ray, whereas a convex lens concentrates collimated light rays. It's just the surface that works in a different way, right? Focal point on the same side of the object. On the other side of the object, mirrors do not have a second focal point. Lenses do have a second focal point that's located in front of the lens. Similarities and differences between spherical sting lenses and mirrors. Okay. for a positive lens, right? For a positive lens, if an object is far away from the second focal point, the image formed will be behind the lens. It will be real and inverted. Now, for a positive mirror, let's do that for a positive mirror, right? For a positive mirror, if an object is far away from the second focal point, far away from the image formed will be in front of the mirror. In front of the mirror, it will be real and inverted. If an object sits at the second focal point f prime, right? The image form will be improper. There will be no image because the light rays do not intersect each other. If an object is at the second focal point of a lens, right? Lens f prime. Focal point of a mirror, the image formed will also be improper. There will be no image formed because light rays do not intersect each other. Okay, and you can let me write that down here too. Another one here. If an object is between the second focal point f prime and the lens, the image is formed in front of the lens, and it will be virtual and straight. We have something similar, right, for the mirror. If an object is between the focal point f prime and the mirror, the image form is behind the mirror. Behind the mirror, and it will be virtual and straight. This is the principle. Okay, this is the principle of the magnifying glass. Okay, here no, we don't need that. In this case, the image will be larger than the object, or the magnification will be greater than 1. Now there is a, here you go. We also have a simulation for lenses, okay? You can go there in the internet and check it out. Let's take a look there. Here we go. Here you go. Here's a positive lens. That's a biconvex lens. Okay, here's my object. I can move it further and closer to the lens. Okay, and here's the magnification, right? H naught, D naught, DI, HI. So here you go. As the object moves further and further away from the lens, the image is formed closer and closer to the focal point. As I approach my object to the lens, the image is formed further and further away from the lens and behind, right? Here you go. Here's the light ray that passed through the center of the lens. The light ray parallel to the principal axis and passed through the focal point of the lens. Here is a light ray that passed through the focal point in front of the lens and is refracted parallel to the principal axis. Okay, note that it is, this image is formed as though as the lens were all, the lens were very large, right? So it is as though this edge of the lens is past this point. Okay. As I approach my object, here you go. As I approach my object, look at towards the lens, the image moves further and further away, and the size of the image increases as well, until it comes to the point when the object sits exactly at a focal distance from the lens. Look what happened. We form an improper image. Past this focal point, the image becomes virtual and is formed in front of the lens. Here you go. This is the very principle of the magnifying glass. Okay? If you have your eye right in here on the right side, you'll be seeing this large image. Okay? Large image, which is larger than that of the object. That's for positive lenses. Now, what you have to know, here go. Let's take a look at the equation again. Here's the equation, right? Remember the following, just like for the mirrors. Convergent lens. Let's see, positive lens and mirrors, right? Positive lens and mirrors. And mirrors. The focal distance is greater than 0. Negative lens and mirrors. Negative. We need the lens and mirrors. The focal distance is going to be negative. Can you remember that? Convergent lens. So the same treatment that we did for the mirror applies for the lens. Because it's just almost the same thing, right? With one detail here or there, that's different. Convergent lens for real objects. We can have virtual objects too, but we're not covering that here, okay? We can also have, we may also have virtual objects, but we don't cover them here in this course. Object placed in front of the lens at a position greater than 2f. Light ray coming from the tip of the object, parallel to the axis, is refracted toward the focal point, passing through the f prime point, f prime focal point, distance f from the front of the lens, is refracted parallel to the principal axis of the lens, passing through the center of the lens, follow an unrefracted path. The intersection of these three light rays define the position of the tip of the image of the object. Image formed is real, inverted, smaller, position of the image is closer to F. Closer to F, okay? Object placed in front of the lens at position greater than position at the position d naught equal to 2f. Here, there was a mistake there. Image formed this real, inverted, same side of the object, and it's formed at 2f. Object placed in front of the lens at the position distance d naught less than 2f greater than f. Image formed is real, inverted, larger, and formed at di greater than 2f. Object placed at distance f, right, in front of. Oh, that's exactly what we have in the simulation, right? Let's go. Let's follow the simulation. Object placed in front of the lens at the position d naught greater than 2f. Here you go. Object here. D naught greater than 2f. Here's the image. Object placed in front of image formed is real, inverted is smaller. Position of the image is closer to f compared to the other images, okay? Image is smaller, right? It's closer to f. As we approach, right? Twice, so let's see. Right in here. Object placed at d naught equal to 2f. That's what I have right here. F is 4, right? Focal distance is 4. So 2f is 8. Here you go. Image form is real, inverted, same side of that of the object. That's exactly what we see here. The size is the same. The distance the image is formed is the same distance that the object sits. Object placed in front of the lens at the position between 2f and f. Okay, between 2f and f. So it should be here. Here's 2f, here's f. Right? So here you go. Object would be larger. Image is real and inverted. Image is real, inverted, larger, and formed at di greater than 2f. What about the distance f from the lens? Take a look here. Just like is improper. Image is improper, right? Object placed at distance f in front of the lens. Image formed this improper. Image, let's say object distance less than f in front of the lens. We're going to have this virtual image. Here you go. Here's my virtual image. In this case, the image is virtual, upright, larger, and formed at di less than d dot. That's what this. So this is a summary of what you saw in the simulation, right? Let's see what about this one here. Okay, so let's take a look at what we covered so far. What time is that? I think it's time for our break, right? 11:50. Yeah, let's take a break. Geometrical sections of the chapter, what we covered. We covered the spherical lens, yeah, scene lens equation. And we're going to skip most of those things. Let's see if we can cover the human eye, okay? And what I want to do, I want to take a break, 11:50 a.m. to 12:05 p.m. Any questions? So I'll see you in 15 minutes. I am back here. Let's share the screen. Yeah, we finished. We managed to finish. We're just not going to cover the optical instruments, okay? With the exception of the human eye, let's cover the human eye. And we can say that the human eye is an optical device. It behaves just like a convergent positive lens. But first approximation, we can say that the lens of the eye is the one that provides all the refraction. That's what first approximation. Okay, strictly speaking, it's not just the lens, but the other regions of the eye as well provide all the refraction of the light. But in reality, okay, strictly speaking, the cornea and the aqueous humor and the vitreous body also has some contribution on the refraction of the light. Uh, the lens of the human eye has this advantage over regular lenses that are manufactured. Regular lenses that are manufactured out there are rigid. And because they are rigid, you cannot change the focal distance of the glass lenses, glass and plastic lenses that you have in there. In the case of the human lens, the muscles of the eye can adjust the radius of curvature of the human lens, and consequently, its focal distance. Okay, think about that, right? The lens, the human, it's something like that, right? Here you go, something like that. The human lens is any lens, right? Is something like that. So whereas glass lenses and plastic lenses are rigid, their surface cannot be changed. The human lens can be the radius of curvature of the human lens can be adjusted by the muscles in the eye. And when you adjust this radius of curvature, this radii of curvature, you do change the focal distance of the lens. However, as we age, the lens becomes harder and harder, does not flex as much, and we lose our ability to focus on objects that are closer to the eye. That's why we have to use corrective lens for the negative lens, the positive lens. That's why we have to use a positive lens, okay? That's why as we age, we have to use positive lenses to visualize objects that are closer to the eye. Here you go. So in short, regular lenses are rigid. However, the lens of the human eye is flexible. And let's talk about adverse conditions of the human eye. Nearsighted and farsighted eyes. For the case of nearsighted eyes, I am nearsighted. What is the problem? Here you go. Let's see if I have some illustrations, right? Let's take a look at some illustrations here. Okay, here you go. Normal eye. The normal eye, we have a lens here, and the image is formed exactly at the retina. In the case of a nearsighted eye, the eyeball becomes elongated, and the image is not formed at retina, it's formed before the retina. So what do we do to correct for nearsightedness, nearsighted eye, a nearsighted eye? We use a negative lens. Okay, the negative lens is gonna make the focal distance, the overall focal distance of the eye longer. Okay, so two adverse nearsighted. Let's write that down, right? Here you go. In nearsighted eye, the image of the object is formed before the retina. This is because the eyeball becomes stretched or longer. A consequence, the image can only be formed before the retina. Okay, to correct for this condition, we use negative lenses that in conjunction with the lens of the eye, result in a longer focal length. So the image can be formed at the retina. Farsighted eye. What about the farsighted eye? Here you go. Here you go. That's nearsighted, right? Here goes farsighted eye. In the case of a farsighted eye, the eye becomes shorter. The eyeball becomes shorter, and the image is formed behind the retina. So to correct for that, we have to use lenses in such a way that the overall focal distance of the lens of the eye and the artificial lens ends up being shorter. Okay, so here you go. That's the lens we use to correct for a farsighted eye. It's a positive lens. And the image is formed at the retina. Okay, so to correct for this condition, we use positive lenses that, in conjunction with the lens of the eye, results in a shorter overall focal length. So the image is formed at the retina. At the retina. That's how we correct in addition, right, to the curvature of the lens, which is affected by the ciliary muscles. It's the ciliary muscles that changes the shape of the lens of the eye. We also have the pupil of the eye that can change its diameter to let more or less light pass. Its diameter can be anywhere between 1.5 millimeters to 9 millimeters. If you shine a very bright light in your eye, you can see that the pupil of the eye, which is that black circle in the eye, becomes smaller, right? If you turn off the light, then the pupil becomes larger to let more light go through the eye. In a dark environment, the pupil becomes very large. And that's, let's see, that's not everything because I have to cover one more thing that I didn't, right? Which is negative lenses. I cover only positive lenses. Let's cover negative lenses. I didn't cover negative lenses here. And we can look at the simulation as well. Here you go. Here's the simulation. Let's see if I can change this guy here. I know that there is a way to change this lens. F, yeah, it doesn't look like we can. We have to donate, drawing light, concave and convex lens. Okay, so in principle, we can change the lens. How do we do that? Maybe here, no. Simulation. Oh, okay, it looks like we have to do that. Let's see. No. Oh yeah, here you go. Now we got it. That's how we change the lens. Okay. Now here you go. Here's my object, right? And as it behaves just like the image of a negative mirror. We have just one solution, right? The image is formed on the same side of the object and is always going to be smaller. See that? Always going to be smaller if the object is real, okay? So negative lenses. I'm gonna put negative lenses right in here. Negative lenses, biconcave, planar concave, and some convex concave lenses. Not all, okay? Negative lenses. Object in front of the lens produces an image that is always virtual. Virtual image in a lens, virtual image in a lens for a lens is formed in the same side of the object, right? Notice that virtual image for a mirror is formed on the other side of the mirror. A virtual image for a lens is formed in the same side of the object. Virtual image for a mirror is formed on the other side of the mirror. So the object is one side, the image is on the other side for a mirror, right? For a mirror, here you go. For a mirror, for a negative mirror, object on one side of the mirror image is formed on the other side of the mirror. Important difference. For a negative lens, object on one side of the mirror, image is formed on the same side of the, not mirror, right? On one side of the lens, on the same side of the lens. Like that. The equations for the position of the image is the same as used before. Okay? 1 over f is equal to 1 over d naught plus 1 over di. So that's what we have to cover here. Let me just go quickly through how we negative spherical lenses, right? Here you go. Negative lens. Principal axis, focal point, focal point. In this case, the focal point is in front of the lens. Here you go. Here you go. For a positive lens, the focal point is behind the lens. Object in front of the lens. Light ray parallel to the principal axis. Diverge. Light diverges and the extension of the light passes through the focal point. Right? Here you go. That's where the red goes. Light ray that passes through the center of the mirror is follows unrefracted. Light rays that points towards the focal point behind the lens is refracted parallel to the axis. And now if you want to find out where the image is formed, right, you have to extend the light rays, and the point of intersection is where the image is formed. The image will always be smaller than the object. So here you go. Image will always be smaller. Image will always be smaller than the size of the object. That's what you have to know. Kind of repetitive of what you get, okay? And so we got human. Okay, we got everything. Everything that we want. We're skipping polarization, lenses in combination, magnifying glass, blah, 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 okay? And now we can say that we can include chapter 26 on exam number 3. Semester is almost over. And yeah, we can start relativity today. There you go. So yeah, that funny theory developed by Einstein, Albert Einstein. Resistors in parallel. Okay, good. And this one here is going to be number 2. And it was very counterintuitive. Theory of relativity is a very special relativity, is a very counterintuitive theory. And it provides some consequences that are very difficult to believe based on what we see in our normal world. Okay, this is the physics of the 20th century. Let's take a look at where the book is for this chapter. Here go. It's chapter 28. We're skipping chapter 27, special relativity, events and initial frames of reference. We're going to talk about that. Okay. So the theory of special was formulated by Albert Einstein in the first years of the 20th century. What Einstein obtained from this theory was something that was both very simple to formulate mathematically, and yet very counterintuitive. The results were so counterintuitive that they were very difficult to believe. The results were so counterintuitive that they were very difficult to believe. It was so counterintuitive that it took a long time for scientific community to accept it as a fact. The Nobel Prize that Einstein won was for his contributions on to Brownian motion and the photoelectric effect. No specific mention was made for his development of the theory of special relativity and the theory of general relativity, even though those would be his greatest contribution. Okay, so you have this funny situation, right? He didn't get a Nobel Prize for this, for the most revolutionary contributions of his. He got the Nobel Prize for something else that was more down to earth, the photoelectric effect and the Brownian motion. There was just a mention that other contributions by Albert Einstein, right? If you go in the Nobel Prize, you go Einstein Nobel Prize, the citation that the Nobel Prize committee, Einstein's Nobel Prize, let's see, Einstein's Nobel Prize. Come on. Not a robot, okay. Was awarded the 1921 Nobel Prize in Physics, which he received in 1922. Contrary to popular belief, it was not for the theory of relativity, but specifically for his services to theoretical physics, and especially for his discovery of the law of photoelectric effect. No mention was made of the special theory of relativity and the general theory of relativity, even though he deserved one Nobel Prize for each of those two contributions, okay? Einstein delivered his Nobel lecture, Fundamental Ideas and Problems of the Theory of Relativity, even though he was not awarded the Nobel Prize for the theory of relativity. He lectured on the theory of relativity there at when he was given the Nobel Prize, okay? In 1923, after receiving the award. Einstein was nominated 66 times before receiving the prize. I didn't know that. Interesting, right? But he won only once. He did not attend the 1922 ceremony, having received it a year later, and instead lectured on relativity in Gothenburg, Sweden, on July 11, 1923, as his Nobel lecture. The money from the prize went to his first wife, Mileva, as part of their divorce settlement. Einstein married his first cousin after he divorced from Mileva. Okay, and let's talk about the laws of physics. So let me get my illustrations as well. Relativity, right in here. Here you go. View, zoom, 200. Let's see. Yeah, too large. Huh? Yeah, let's see. Yeah, you gotta maybe 150. Yeah, let's keep like that. Illustration of relativity second. Okay, let's talk about the postulates of special relativity. And but before we talk about the postulate, let's talk about what are the laws we have introduced to you so far. Okay. Laws of physics introduced so far. Introduced so far. One. Newtonian mechanics, 3 laws of motion. In reality, there's only 2 laws because the first law is just a consequence of the second one, plus the law of gravitation, right? So it would be a total of 3 laws overall, 2 laws of motion and the law of gravitation. Then we also have in thermodynamics, we have 4 laws. The zero law, the first, second, and the third law. In electricity and magnetism, we have 4 laws again. Gauss's law of electric and magnetic field, Ampere's law, and Faraday's law. All those 4 laws are known as the Maxwell's equation. In ray optics, we have the law or postulate of least time, the refractive index law, and the behavior of light as a light ray. In special theory of relativity, we have only 2 laws. Okay, why is it called a special theory of relativity? There's a reason why Einstein called it the special theory of relativity. And the other one, versus general theory of relativity. Okay, let's see. Versus. Okay. This one is more powerful than the other one. Okay. The second one is more genetic than the first one. Consequently, it is more powerful. But the main difference is that special theory of relativity, special theory of relativity applies only to referentials that move with constant velocity. Okay. General theory of relativity applies to a referential, right? That are accelerated. We have 5 more minutes to go. So referential that is accelerated, right? That is accelerated. Constant velocity, constant uniform motion, uniformly or accelerated motion. Let's see, someone is trying to join us. Okay, here you go. Keep that in mind. That's the so just before Einstein, historically speaking, the beginning of the 20th century, right? Physicists thought that they had discovered everything that they could have discovered. They thought that they're done with physics. Little they knew what was about to come. Okay, they thought that they had all the laws they needed to explain the universe. That's because Newtonian mechanics, thermodynamics, geometrical optics, the laws of electricity and magnetism had been extremely successful. However, physicists start to find holes in their understanding of the universe. And the theory of relativity ended up being one of them, one of the holes that they could. In thermodynamics, for instance, okay? In thermodynamics, they could not theoretically explain the problem of the black body radiation, the so-called catastrophe of the UV. I'm not going to get into details, but that was one of the problems that they had. On the top of that, they could not measure the motion of the ether using Michelson's interferometer, a very important device, very important device that earned Michelson a Nobel Prize. At that time, scientists believed that the vacuum of outer space was filled with an ethereal substance that was required for light to propagate. This substance has some unusual characteristics. However, this theory of the ether started to fall apart when Albert Michelson failed to measure the relative motion of the ether. Today, we call this failed experiment the most successful failure in human history, okay? So, a failure that's considered the most successful one in human history. It was because of this failure that scientists start to reject the existence of the ether, an unnecessary assumption. At that time, scientists also thought that there was this absolute referential system in which everything else had to be measured with respect to the so-called, scientists thought there was this absolute referential system, which was the ether, okay? Against which everything else had to be measured with respect to. Should be the ether that would be in absolute rest. Okay, and then came Einstein and he proved that there was no such a thing as an absolute referential in the universe. This theory, the assumption of the ether, right? The assumption of the ether was necessary because scientists thought incorrectly that light required a medium of propagation. For this reason that the ether was invented. For this reason that the ether was invented. For this reason, the ether was invented okay, was invented to justify the propagation of electromagnetic waves. So this was an incorrect mindset, okay? We have lots of, lots of cases in science. We have this incorrect mindset that do not allow us to progress. So this was an incorrect mindset, since we know that electromagnetic waves, since we know today, right, that electromagnetic waves can propagate in vacuum. That was the historical background when Einstein came along. And he go, and that's and then physics came into a crisis. Okay, for this reason, comma, they were trying to match the relative motion of this absolute differential with respect the relative motion of this absolute differential with respect to the motion of the Earth and vice versa. And Michelson invention, Michelson interferometer was a device that was sensitive enough, was a device that was sensitive enough to allow this type of measurement. For Michelson's surprise, okay, he was never able to measure the relative motion of the ether with respect to the Earth. He got negative results over and over again, results that nobody were able to explain at the time, results that nobody was able to explain at the time. Until Einstein came along. Okay, until Einstein came along. Okay, Einstein simply said, look, folks, there is no such a thing as a absolute referential frame of reference. There's no such a thing. Okay? Here on Earth, we are led to think that the absolute frame of reference is the ground, right? Because the velocity of your car is measured with respect to the ground. But there is nothing special about the differential of the ground, about the differential of the freeway. And that's what Einstein said. Look, folks, there's nothing special about this so-called absolute frame of reference. The ether was an unnecessary hypothesis. Every motion, Einstein came further, went further. He said, every motion must be measured with respect to another referential instead of this absolute ethereal referential. This gave rise to Einstein's first postulate. Remember his two postulates, right? The postulate of relativity. The laws of physics are the same in every inertial frame of reference. Has to be inertial frame of reference, not accelerated. And there's nothing much of novelty here, because Newton's law also, right? They are formulated with respect to a inertial frame of reference. If the frame of reference that you use is not inertial, then you have to make an adjustment to Newton's law of motion. Okay, so this first postulate was not that much of a surprising. Okay, what was surprising was the second postulate. Not only surprising, it was also very difficult to swallow. which was very, very difficult to swallow because of its consequences, okay? We have 5 more minutes to go. Not because of its formulation. Its formulation is very simple. The problem was the consequences of this postulate. And what is the second postulate of Einstein? The most important one, the speed of light postulate. Einstein stated that the speed of light in a vacuum, measured with respect to any inertial frame of reference, will always be 300,000 kilometers per second, no matter how fast the source of light and the observer are moving relative to each other. Okay, I want you to understand this postulate, and I'm going to illustrate it. I have an illustration here. Here you go. Illustration of relativity, second postulate. I have to zoom out. This one here. Zoom. Yeah, okay. Consider a referential that is at rest with respect to us. 4 more minutes to go. Okay. I come up and put a laser source there at the origin of my frame of reference. And turn on the laser beam. Okay. Then I put a detector that rests with respect to the laser source. And it's to measure the speed of the light. It's possible to do that, right? To some instruments out there. Like the microscope interferometer, we can use the microscope interferometer to measure the speed of the light. Referential at rest with respect to us, and the detector too, right? Both the detector and the laser are at rest with respect to referential A. What happens in real life? This detector measures a speed equal to 300,000 kilometers per second, okay? Now we are going to repeat this experiment in a different way. 3 more minutes to go. We are going to put this detector, we are going to put this device in a car, in another referential, in a train, whatever, that's moving towards the laser beam. Okay? This is one of the consequences of Einstein's postulate. When we do something like that, the detector still measures the speed of 300,000 kilometers per second, not 300,000 kilometers per second plus the velocity, the speed of the referential beam. That is the surprising part of Einstein's second postulate. People would think that the measurement of this detector for the speed of the light would be 300,000 kilometers per second plus VBA. That's not how nature works, okay? And then you repeat this experiment, okay, here you go, with the detector moving away from the laser. According to Newtonian mechanics, okay, to relative velocity, you would expect that the speed of the light would be measured, would be 300,000 kilometers per second minus VBA. But no, you still measure a speed of 300,000 kilometers per second, okay? That was the surprising result of Einstein's second postulate. And you folks need to believe that. And it doesn't matter. It doesn't matter if it is the detector moving towards the laser or if it's the laser moving towards the detector. It's still 300,000 kilometers per second. Okay? Even the laser moving away. So that's what I want you to understand. That's how the postulate works. Nature behaves this way, by the way. And we can stop right now. It's a good point to stop. It's already 12:50. Do you have any questions about that? So I will see you Monday, and I'll have my office hours right now. Okay? See you. Oh, Monday, no, Wednesday, right? See you on Wednesday, the day after tomorrow. Bye-bye.
Thank you.
I'm going to stop recording. Let's see. Thank you, Jason. I'm going to stop recording here. Record.